The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show. In this week's episode, we're going to resume working on the mini pinball machine.
All right, so we got the pinball boards in. I'm gonna go ahead and populate one of these, see how well it turned out. And if there are any mods that we need to do, I'll go ahead and do that. And then update the schematic if necessary.
Okay, I did design these boards pretty quickly, so they might not be perfect. So yeah, let us know how that goes. While you're working on that, I'm going to be doing some sensor work. Now, we've shown in previous episodes, we might have a target that gets hit and has a microswitch. We might have a pop bumper with like a little ring around it that conducts electricity. But I was also thinking maybe like a rollover switch that's infrared, like a emitter detector, and the ball rolls over it and bounces IR light back down into the sensor, and it's like, oh, a ball.
Yep, give me the signal back, okay.
Right, so we have some new small surface mount parts to do that. So I'm gonna test those out on the circuit, and if it works, I'll design a little PCB around it. All right, and then once I have the switches done, we can hook them up to your wired board and see if it gets the data properly.
All right.
Let's get started.
Amazing hacks.
Should we take it for a spin?
Inspired designs.
Imhotep's priests.
Regrettable acting.
No one seems to get it.
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
In a previous episode, I worked on a PCB design for the mini pinball game. And I laid it out very quickly, I think in like, what, one day?
Something like that.
So it turns out there were mistakes.
Yeah, these things happen.
So we needed to put in some bodges on the board. So while I've been working on other projects, Felix has been slowly bodging the board into a working state. So Felix, tell me about all the errors I made.
So first thing I did, I checked the GPIO and the LEDs, and I realized that the GPIO needed to have pull-ups on them, and then also for a number of the LEDs, they weren't receiving power.
The power connection is
missing. So I linked those over. And then I got to testing the LCD.
Wow.
And discovered that it has a different power supply voltage.
For the backlight.
Yeah, it takes, what was it? I think it was 6.2 to 6.8.
Oh no, I forgot the potentiometer for the contrast.
Yeah, you had some pads for resistors, but I just put that potentiometer in instead.
Idea. Yeah, that makes sense. All right, what is this?
Okay, so this is my little rig to get the 6.5 volts to turn on the LCD.
So you're using a variable power regulator?
Yep,
Okay.
I set that up to 6.5. It's a LM317, I believe.
Okay.
Yep.
And then you talked about the 5-volt regulator getting pretty warm?
Yeah, I noticed that it was really hot. We're taking 12 volts and knocking that down to 5, and we don't have a lot of...
It's a linear regulator, isn't it?
Yeah.
So when you have a linear regulator, basically any power difference is turned into heat. And if you have a lot of surface area on your board or a lot of copper or heat sink, it's not really a big deal, but a better way to do it is with a switching power supply.
So I put that into the schematic.
Yeah, I see it over here. And then you have, you have a coil on top, then you have some of the other parts on the bottom there?
Right, yeah.
Okay. Where's the variable power supply on this?
Well, actually, I found a regulator that puts out 6.5.
Oh, really? From 12?
Yeah.
Is it also a switcher?
Yep, and that's underneath. There's also additional components for that as
Oh,
well.
okay, so this is the 5-volt regulator, then you have a 6.5-volt regulator underneath. I wish we didn't have to do that, but
I feel the same way.
I guess we wanted this big screen.
Yeah.
Okay, so we still have the same filter caps. We've added a coil here as an inductor for the switcher. Is there another inductor on the bottom?
Let's see here. What did I do for that 6.5 volts? Here we go, this part right there. It's a switching regulator.
Okay, so there is an inductor on it.
Yeah.
Is it a surface mount inductor?
Yes.
Okay, because the one you have on the front looks pretty large.
Yep, that's for the 12, I believe.
Can you turn off the top layer so we can see it?
Oh, here, let's see this? We have presets.
Oh!
Check that out. That's actually
Oh, so you can just
cool.
change a whole bunch of things at once?
Yeah, that's
Oh,
nice.
so you got a big shocky diode there.
Yeah, there's that. What
Is that the 6.5-volt regulator right there?
Yes.
So the big changes were to the power circuitry
Yeah.
and then some bodges on the screen.
That was a major change right there.
So the screen threw us for a loop. But now with the switching regulators basically switch on and off very rapidly to create lower voltages, which means they're very efficient, which means you're not wasting voltage potential as heat.
Right.
Okay, so what about the audio amplifier? Does that work?
Yep, the audio amplifier works. I had a little trouble soldering it in there. I probably should have used
The oven?
Yeah, used the oven, but I already had all this other stuff on there by the time I got
like some of these would melt in the oven.
Yeah.
All right, so I'm going to take the emitter and I'm going to solder it right here. So I'm just doing this by hand before I bother designing a board. Now we should be able to see if the emitter is working using a cell phone, although depending on the manufacturer, some phones have IR filters and some do not. Like I believe Apple phones always do. So sadly, as our phones get better and better, you lose certain abilities like ability to see infrared. Stupid magnetized tweezers. Does that super metal go all the way through your body? All right, so there's the emitter. Okay, so the ball is 5/8 inches, so I think if we go half that, let's go 0.3, that's roughly half. And it lines up to a standard circuit board grid. There we go. All right, so when we're looking at it from the top down, okay, so pin 1 is the emitter, pin 2 is the collector. I need to find something that can see this infrared. Let me see if my phone can do it. Does the Google Pixel have an infrared filter on its camera? Let's find out. Yeah, okay, it's lighting up. The Google Pixel doesn't have an infrared filter on its camera. It's definitely illuminating an infrared. All right, so now we should be able to get a reading off of this. So regular white light, it contains ultraviolet and it also contains infrared, some infrared. So if I block this with my finger, I should see a difference on the meter. See that? So when I block light from hitting it, it increases the resistance. Basically, it's not, transmitting current as well. All right, so we know the emitter is working. We know that the detector is, seeing a variance in the amount of infrared hitting it. So let's go ahead and power this up again. And then I'm going to put the multimeter to voltage, and then we'll look at the voltage change. So we're pulling up the photo transistor with a 10K resistor. We're pulling it high. Then we're going through a 1K as our sense pin, and the other side, the emitter, is going to ground. So let's turn on the power. Okay. That is not what I was hoping for. Weird. I better double check this. I still think it's a cross-contamination issue. The fact that they're side by side, enough infrared is leaking to falsely trigger the sensor. As an example, okay, so here's the sensor just hooked up by itself. The infrared emitter has been deactivated. So we got 0.42 volts, which is not a big deal. Most of that's coming from the overheads. It's still well within the threshold of being considered a low by circuitry. Okay, so here's just a random infrared LED. So if I point that at the sensor and turn it on, boom, it jumps up to 5 volts. Yeah, so maybe they're too close together. I mean, granted, we're talking about having like a piece of wood or something separating it, but yeah, it's really strange. I didn't think there'd be that much cross-contamination. I could also try putting a larger resistor on the emitter to lower its power even more. That might help. So yeah, but at least I know it's not the detector, it's the emitter. I put some clay between the emitter and the detector. I don't think Clay Aiken would fit between the emitter and detector. Ant-Man probably would. All right, let's see if that makes a difference. Yeah, it's a better nominal voltage, 1.44. So if something reflective goes over it, it should increase the voltage. It's not bad. Let's see how skin does. Yeah, not as good. I should get an actual pinball. Here's a 5/8 pinball. See, if you go too close, you don't really have enough room to reflect, but if you pull it back a little bit, see how the voltage goes up? That shows you the amount of reflection of the pinball. It's close, far, close, far. Now it's 6mm wood, so let's check 6 millimeters of distance. 6 millimeters isn't that far. It's not much higher than the clay. Be right about there. Yeah, that's not as good a result. I mean, I'd rather see 5. That still needs to be lower. 1.44 is kind of on the edge of what would trigger as a high. 1.5 volts is usually that's usually what the threshold is. So anything below 1.5 will count as a low. Anything above will be a high. I've hooked up 2 different voltages to this test circuit. I have 3.3 volts on the phototransistor and only 1.6 volts going into the emitter. And it is giving me better results. I got 0.94 open, reflect gets me about 3. I would kind of like it to be lower when it's open, but it's still within tolerance of a TTL high or low signal. Basically, you're looking, going past 1.5 would be the rule of thumb. Of course, this is a flat surface of a piece of steel. This reflective surface probably not going to work as well because it's going to scatter the light in more directions. Yeah, see that? So what I could try doing in this case, could try slightly increasing the voltage of the emitter, but that's going to cause the low level to go up. See that? Look how quickly that rises. So the problem I'm seeing here is if we turn the power up, we get cross-contamination between the emitter and the detector. If we turn the power down, which is what we're doing right now, the surface of the pinball is too random to reflect light back consistently. Whereas if you have a flat surface that's reflective like this dial caliper, you get a better result. I'm going to bump it up to like just, yeah, see how quickly that scales? So our 1.4 volts through a resistor, so the forward voltage is going to be even lower than that on the emitter. So the emitter doesn't take much at all. So we're reflecting the IR back into the detector and causing it to saturate the photo transistor and, you know, basically give us a signal. I think this needs more thought. All right, take a look at this. See that? 3.24 volts. Now I'm going to put the electric tape divider in. Wow! So there is a lot of cross-contamination horizontally. Now let's put a pinball over it. Hey, that's a pretty good result. I should put it on the scope and see just how fast it can react. All right, so I just got it hooked up to the scope here. Let's go 1 volt per division. Pretty good jump there. What I want to do is I want to create a fast version of it. So I'm going to like hypnotize it like this, right? So I'm going to set the trigger on the scope to trigger on a high point level. Let's go 1.5 volts. Great. Run single. Hey, if we had it hooked up to Alexa, she could do it for us. There we go. There's a capture. Let's see how wide I can get the scale on this thing. There we go. See those pulses? He's dead, Jim. My God, I don't even know his anatomy. Do your hands shake, doctor? The oscilloscope is much, much, much faster than this meter. I mean, this is a high quality meter, but it's no oscilloscope. So by putting this onto oscilloscope, we can see, you know, what our peaks and valleys are. And yeah, it's pretty good. Let's take a look at the timing here. It's a 40 millisecond long event, but the actual trigger time probably going to be less than that. It's actually above the threshold. It's going to be about 20 milliseconds. I mean, we can't just look at the whole slope. We have to look at the halfway point. So the halfway point past the 1.5 volt peak is about 20 milliseconds wide, which is still pretty good. I guess I got to run some more iterations here. Yeah, but that's an eternity to a microcontroller. So yeah, I don't think it would have any trouble actually seeing this. Hey Felix, you remember what frequency we were scanning the switches at? My point is, so like if the ball is moving really quickly, you know, past this, of course, these switches are probably going to be a little bit further back, so the ball's going to lose some of its speed. So I just want to make sure that the system can detect it. I will help you come back to life. Yeah, so we're looking at about 10 millisecond pulses here. I'm pretty sure we can see that even with the slower Arduino. I'll double check the code just to be sure, but yeah, so this pair with the proper voltage and some sort of dark isolating block between them, in this case a piece of electrical tape, does give us a pretty good result. We have very close to 0 volts when inactive and then 3 volts when active with a pretty good pulse. I mean, it's a short pulse, but it'll be enough. Basically anything past 1.5 volts should trigger as a 1 on the microcontroller. I finished designing this really small 2-sided circuit board. On the top we have a 1206 surface mount LED. We also have the emitter detector pair right there. The appropriate resistors are on the bottom and a place for a 3-pin header, kind of like a servo. And also a place to put a screw. So when we rat's nest, it looks like this. So it's got the flooded ground plane there. So now it's time to do some laser paint. So I'm going to go over here into Adobe, and I have a little bit of double-sided copper clad left with paint on both sides. So this represents the area that's free, and then we have mounting holes in the router. So this is the safe cut inside of it. So 5 by 5 I think I can do. And this is what it's going to look like after we cut it out with some nice tabs. So the reason I'm doing it on the CNC machine is so I can get a perfect 5 by 5 inch square, which really isn't possible doing it by hand on the bandsaw. And the reason I want it to be perfect is so, since it's double-sided, we can laser etch one side in a jig on the laser cutter, flip it over, and then laser etch the other side. And since it's you know, nice and straight, that way we know when we flip it, everything will remain lined up. So yeah, let's cut this out and then we can laser it up. I've started stuffing these test boards that we laser painted. This one is going to be an IR pair, and then this one's going to be just a regular light board. So I've got this little surface mount LED here. This is a pretty small part. So I'm gonna figure out the polarity, okay. Then hopefully not lose it because of my magnetic tweezers. This is why machines should do this, not humans. There's no solder mask on our board, so if my solder strays, it'll stick to more copper and cause a short circuit. Now on the back, we have a couple spots for resistors, although we don't actually need that for the light because the light has an external single resistor back on the driver board, which controls the current for all the lights. However, if we just try to power this, I don't think it's gonna work yet. Yep, it's not working. Because, like I said, our vias are not plated through hole. So even though I soldered this header in place, it's not working because the trace back here needs to connect to the header, but it can't because the via is not connected. So I actually need to remove the shroud and solder it on both sides, all without cutting myself. Okay, see now if I put solder here, then that should complete the circuit. Again, with a real PCB, through holes be plated, and I wouldn't have to do this, but we don't have a real PCB. We just have laser paint. So the idea here is you'd send 5 volts to all these modules, and then you return the ground of the LED, and that goes into the Texas Instruments LED controller chip, and then basically once it syncs the ground for a certain light, the light will turn on. Let's see if it works. Yay!
Hey, so I just wired up our little laser paint board here with our infrared emitter and infrared detector, and connected it to our prototype pinball board here. I got it on switch number 3, and our display here is showing us our version of our program here, but then you see all these ones at the bottom here. There's 16 ones representing the switches. So if I take my screwdriver here and I close one of these contacts, it turns the 1 to a 0, right? Indicating that the switch is closed, okay? So let's see an example of this. I'm gonna shoot for 6 millimeters away from there. Oh, look at that. Because 6 millimeters is going to be the thickness of the plywood here. But look at that. So we go from 1 to a 0, indicating that the ball has passed over the emitter detector pair and giving us a signal. So this works pretty good.
That's all we have for today, but to recap,
I populated the board. I found the mistakes, I made some bodges, a few things we missed, and then made corrections on our board. We're going to send off for a new board. And also, we made a laser paint of a new circuit for the inserts and the IR emitter detector.
Yeah, so it's one little PCB, but it can do 2 different things. It can either see the ball or it can light something up. And we tested it with the board, and it worked great. So we could probably send off for some small PCBs of that design as well.
That'd be excellent.
So in the next episode, we're going to take the physical design from this motherboard and build it into the case. So we can put everything together, the flippers, the playfield, the motherboard, and see how it fits together. See if it got way too big, see how it fits, is there room for the buttons, basically mechanical design.
What did you think of our pinball board design and our switch design? What would you have done differently? If you have any comments, please leave them at the Element 14 community at element14.com/TBHS.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. These smart arms can place surface mount components in an environment no human hand could enter.
The unbearable, frightening stupidity of the chicken.
I do not know what the chicken is thinking. Its mind is like a trap, and for my soul, look at it in its eyes, a blank stare of ineptitude.
Your mom's a skunk. I'm telling you, if someone could figure out the 3D printer for PCBs, oh man, they would make out like a bandit.
That one night.
Oh, you want me to get all my rich friends to invest in your candle making business, babe? I see 4 lights. It's time for the Jedi to end. Do 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 do.
Felix built this with a box of scraps.
You will become under my spell. Okay, we're working on mini pinball again. In the previous episode, we made the opto interrupter switches so we could see the ball moving around. So now it's time to make the enclosure to figure out how everything comes together. Felix, what are your thoughts on this board? So this is gonna go right about here. Okay, so here's where the rubber hits the road. Watch this.